like the amount of homework you have to do with those. Get started.
So you got the pipe here, and the diameter is given, the capital R, 0.2 meter, 2 centimeter is this much. So if you say the diameter is twice that, right? Like it's like this big. So it's like a real big pipe. And the velocity profile, as you can see, is given by the radius. Where is the what's my velocity? You see, your reference for velocity is just center. If I want to get velocity here on top, what should I put in the formula for R?
0?
No, I want to get it here. My reference is here. What should I put?
Oh, 0.2.
So if you put point 1, 0.2, which is the radius, the maximum distance from the center, what do you get? You get 0. You can verify. And if you put again 0.2 here, you get 0 here. Why? Because it's just a radius. So you don't have negative R positive. R is always positive. If you 0, you have the center. If you're positive, your R over this cross section. In fact, you can draw it in 3D. If you look at it, your velocity profile is something like this. As you can see. And that's your pipe. And this is center and this R. So you see all over this surface, when you put R.2, what do you get? Velocity 0. Why do I get velocity 0 all over the surface of pipe? Why?
Because there is no velocity on the surface?
Why? Because there is a wall. You know, you mentioned that. It's a wall, all the molecules are attached to the wall. You have this in the third chapter when you have the wall and the flow is going this way. The velocity here was what? 0. That's because of that. All right. Now the question is asking for to find Q. Volumetric rate that passes through this surface. So pick one of these faces here. There you go. Call it A. What's the volume passing through? A. Can you tell me? Well, go back to your notes and you see that we have this formula. Q is equal to VA. V dot A. And if you didn't really understood the derivations, because this course requires a lot of practice, a lot of understanding. If you just look at your note and say, well, all I need is to get my B and put my A and do dot product. And you say, well, what B should I put there? Should I put the velocity here? Here? Where? Which one should I put? And then you say, well, you didn't explain it well. I'm confused. Well, the thing is, this class is only 50 minutes. I wish I could explain every single problem in the book, but I can't. You have to, when you go home, you have to go over all the derivation. You see, I did a lot of derivations. Those are done for a reason. It's not just to show you fancy mathematics. They are done for a reason. So you have to go through all those derivations just to be able to solve the actual problem. So if I give a problem like you, if you don't do the derivation, you really don't understand how I got this derivation. But if it happens that you went through all those derivations, then you realize, oh, okay, this was considering just one element on a surface. The velocity here is say v, and this was dA. And in finite version of this, you get d dot dA dq. That was we had, and then we integrate that. So yeah, at every point, if you make an infinitesimal area, exactly like we did before. You remember I draw that potato? And everywhere we have a dA, and we have the velocity. And we draw all the general form of continuity. Now you have to start from there. You can't start from the most simplified version when your area was uniform. Or the velocity. This is when the velocity is constant and the area is uniform. You don't have curvature. Right? So unfortunately, you can't start from here. You have to go back to the general form. But the general form was, you need to sum them all those tiny elements on the surface, to get your Q. That's it, because that's your stuff from here. Now, starting from here, you get Q is equal to integral over surface. And of course, every time integral over surface, how many integrals should you add? Two. For volume, 3. 2 integral. And I know it's only over this face, right? Now, let me ask you a couple of questions. Do I need to put a ring here?
It's not, you put the ring if it's closed up.
That's right, that's right. See, when you see the ring, that means you close, that means I was integrating over this, and this, and this, and this. And if I put the ring from the physical problem, before even do the integration, the mathematics, if I put the ring here, what would be the result? 0. The net mass is 0. Why? Because it's incompressible. Nothing is compressing here. Nothing is accumulating. Everything coming here is exactly whatever you need. So there is no ring here. So integral over surface v dot dA. V velocity vector v dot dA. Or what we did in the node, if you go to the previous classes, integral over that surface, v dot n normal vector times ds. This was the notation we used. Now this is more convenient. Why? Because all you need to do is to find normal vector there, to find the velocity vector, and do dot product at any point. So look, at any point here, at any point, what's my normal vector? Let's say you put your x, y, z axis here. You put your x this way. You put your y this way. You put your z here, right? So what's if I say over only this face? I know the normal vector is this. But what is my normal vector in this coordinate system? Can you tell me?
J.
Positive j, right? So this guy in that coordinate system as well. What about velocity vector? if you want to make a vector, what did you need? It's magnitude times unit vector in that direction. You can create any vector with a magnitude times unit vector in that direction. So what should I write for velocity here?
Magnitude
Uh-huh.
of
Which
V
is?
A hat,
What's the magnitude of V?
3 times 1 minus 25 r².
Yeah, 3 times 1 minus 25 r squared. That's the magnitude of velocity times. Times.
Yeah.
What's it? So do dot product of these two. What do you get if you do dot product? So you get integral set what do you get for that? Integral over surface. This vector dot that. So you do j dot j. What do I get for j dot j? 1. So 1 times 3 times 1 minus 25 r squared. dA. 3 times 1 minus 25 r squared dA. So in fact, you don't even, or ds, you can call it ds. I mean, we're talking about area. Some people call it dA, some people call it ds. We call it ds on our note. So to be consistent, I'll put ds there. All right, so basically, you don't even see the vector. Why? Because after dot product, they reduce to a scalar. So I need to do that integral. How many different ways I can do that integral? A lot, a lot. One way I do that is I just consider elements, so I just draw them again here. I mean, if we could teach calculus here, if I could teach calculus here, the engineering student myself, we would have something like this in the calculus, the first semester for you guys. So right now, I really don't waste my time. I should not waste my time on things like that, how to compute the integral. I could have gone to more advanced things in the book and give you more benefits. So when you graduate, you have better tool bank. You know, well, unfortunately, I have to stop here and show you how to compute this simple, extremely simple integral. If I don't do that, then if I give you the midterm, I'm not going to give you something like this in the midterm. It's going to be definitely totally different. And there is nothing on check or on line that is indicated. Right? It's totally, I just do handwriting things. You can't even image scan it or image search it online. So you really need to understand it. So I want to compute this integral, and for that, if you know the calculus, you know that there are different ways to do that. One way is to just look it from this direction to this cylinder, and you only see a circle. And then this is the center, and this is your element. You see that? Call it dA or ds in our terminology, ds. The tiny area of this ds. Now from here to here is what? In the cylindrical coordinate is what? R. And from here to here is what? The arc length?
Theta.
The angle is theta. What's the length of that?
R.
Edwin, what is the length of this?
Extensions are,
Huh?
those big extensions are spacing out.
In cylindrical coordinate. Let me drive it a little bigger. That was my fault, I didn't drive it. So that's your element at the R, location R. Right? So from here to here is what? R. And I know from here to here is what? dr. Why? Because you see it's like sweeping. You just sweep your R just a little bit to get this area, the final element, that final space. Now my question is, how much is this R from here to here? If this angle is d theta.
R R d theta?
That's right, R is this side is R d theta. So if I approximate that guy with the rectangle, so let me draw the rectangle here. One more time, zoom on it, you're gonna get something approximately like that. It's not a perfect rectangle, this is smaller than that. But you can say this side is approximately R d theta, and this side is what? dr. You agree? In infinitesimal calculus, if they're really infinitesimal, this is approximate rectangle, these are almost same. R d theta or dr. So what's the area of this rectangle? ds is what? R d theta dr. That's it. So plug it in here. Right? Plug it in here. What do you get? Double integral 3 1 minus 25 r squared. So what for ds, what should I put? R dr d theta. So can you tell me r from where to where? R from? Let me ask. Let me ask. Can you tell me what is the range for r in that double integral? One is theta, one is r. Right? This one is theta. The other one is r. R from where to where?
Not for sure.
Okay. If you are not sure, just say skip or not sure. Right? That's what we're. I'm not going to evaluate you. The purpose of this is called feedback, class contribution, things like that. If one don't ask for feedback, that's not good teaching. You have to ask for feedback. No, what's the range for R?
Is 0 to 0.2.
Is 0 to R max, which is 0.2. What about theta? Emily, what's the range for theta?
0 to 2 pi.
That's right. Thank you. I know you guys know it, but you don't want to say it. Alright? That's it. Evaluate that integral. What should I do for that integral? Well, separate it. They're not dependent. So you just say integral from theta 0. Put it this way. Put r outside. R from 0 to 0.2. Then you have 3, 1 minus 25, r squared, r dr, right? And then inside the integral, you have integral theta from 0 to 2 pi, and then you have d theta. All I did, I just separated, because they, like if this inside this r you had a function of theta, you could not separate them. So I separated integral from 3 times 1 minus 25 r squared r dr from 0 to 0.2, and then theta from 0 to 2 pi integral. So what do I get for this integral? This one is just 0. What do you get? 2 pi. So in fact, you could bring that, put it in front of it, and say just this is the result, is just 2 pi integral 0 to 0.2, 3 r minus 75 r to dr. And then what I did, I multiply 3 and then bring r in, so 3r, and then minus 3 times 25, 75 r cubed. Yeah, from 0 to 5. Now, you go for this, you get what? You get 2 pi, let's do the integral, 3 r squared over 2 from 0 to 0.2 minus 75 r4 over 4 from 0 to 0.2. That's it. And you get, of course, you get 2 pi, 1.5 times 0.2 squared minus 75 over 4 times .2 to the 412. That's one way to do the integral. Another way you can do the integral, you say, well, you know what, this is my ds. Going back here, you see that's my ds. I needed to find something for ds. So instead of getting this integral, this element, which was finite both in r and theta, I could just take it like an infinitesimally thin ring, like that. There you go. And this thickness of ring is what? dr. It's very thin, dr. But the radius at this point is r. So in that case, you would substitute the area of this ring because your element is just so tiny, so thin. So you say, what's the area of this ring? Can you tell me? It's just the parameter, which is 2 pi r times dr. You agree? You see, cut it from here and then unroll it. If you unroll it, you get an element like here. This thickness is what? dr, the length is what? The parameter, 2 pi r. So if you do that, then your integral, everything is in terms of dr. You don't have d theta. So you get one integral. So you convert double integral to one integral. But it's nothing new. It's just the same thing. Here, you see I got 2 pi r dr. That's just a special case of the general double integration. All right, next problem is you do this problem. All right, here. Find VD. This is actually a very practical design problem. So you have some sort of mechanism or tool to compress the air. So it's composed of this large, non-deformable beam that is, you got a slider, this frictionless slider. And then it's over this belt, and then what you do is you apply force here, and that's gonna cause this piston to go up, right? There's no friction anywhere. And then we cause the compressed air. So air is going, there is a nozzle here, air just exits the nozzle. Now the question is, if I measure the velocity here, 1 centimeter per second, how much is that? 1 centimeter is this much. So I go every second, I go this much down. So the velocity is very small here, right? How much velocity do I have? The fluid exiting from that. I'm not going to give questions like this in detail for testing. Right? But I just want to show you how easy it is to solve this. If you understand the derivation part, the mathematical proof. Now, for this problem, I do my 5 steps. Choose system, you write FED every time, no matter what course you have to do that 5 steps. Now, what is the system or control volume here? I'm pretty sure you can tell me. If I want to solve this problem, what should I choose as my control volume?
Cylinder.
This area, the cylinder, right? So let's put a dash on it. So for this cylinder, that is my control volume, or CD, or we call it previously vectorostatic system. But system, they're saying, the control volume. We already mentioned why. Now, here for this system, if I can isolate it, let me isolate it here. So you're gonna have a cylinder like this, and the bottom one is like that. But also here, you get a cut. And you know that the fluid is leaving from here, and this is BD. Now you know that the actual real life thing, the velocity versus this Y, we have changed, right? Here the velocity is 0, and then the velocity maximum in the core, and then go back to 0. You know we have that, right? Well, let's say this dimension, the diameter of this hole is so tiny, the velocity are almost same. I mean that parabolic distribution is so sharp that the velocity is just constant everywhere. So the velocity, I'll put it like this, everywhere just be on this tiny surface, right? Maybe. And the density of fluid is also constant. But look, my volume is compressing, is expanding. So I have that. Why? Because this piston, at this point, I don't see it, but later on, versus time, is expanding. What does it mean? The mass per volume changes. Well, that's exactly what it means. So, if I find the velocity of this point, V at A, if I know how much my dA is, I know how much compression I have. And then by applying the continuity equation, I can find a relation between that and this. Well, how can I know the velocity at this point? Who is Weber?
It's a lever.
Huh?
It's a lever.
So can you write the equation for velocity at that point?
Well,
Let's say if I give you, this is 1 meter,
yeah.
and this is 4 meter. Now, can you tell me how much that velocity is?
Or, 4 centimeters per second.
Yeah, you can. I'm pretty sure you guys have dynamics, course dynamics, kinematics. It's just the easiest kinematics. So, we go back all the way to the velocity at C. And what do I have for velocity at C? So from that, a chain reaction, you find velocity here, and from velocity here, if you apply the correct form of continuity, you get velocity at C. But you go back to your node, let's assume that you memorize, you get this. 0. This is the continuity form. And say, well, I have to do that, right? And say, well, because velocity is constant over that space, area is constant, right? I can do that. And then you apply velocity constant v times area here at point D. So you get BD, AD, and then you see there is no fluid leaving. And say the sum of this must be 0. So you say, therefore BD is 0. And then you go to the next question. But look, is this the correct form of continuity equation? What did you do to simplify that? So you have to say, well, you know what, I think it's messed up. You go back from scratch, the most general, glorious way of continuity equation. What was the most general, glorious way of continuity equation? ddt rho dv volume plus surface integral rho v n ds 0. That was it. And I took this dt inside, but you can keep it outside the entire integral. That's the most general form of continuity, and I'll show you why we got that. It's not just that you can understand it. You may say, well, I didn't really understand. Well, you have to spend 3 weekends just to understand that single line. It's just crazy how much time you have to waste on the course. Right? All right, so let's start with that. Let's start with that. Can I get rid of this then now?
Yes.
Yeah. Because we're assuming constant. What?
Yeah.
Over this control volume, right?
Oh.
The thing is, this is what? This is going to be the rate of changing the volume. If I write my volume here, let's do that. It's going to be rho times that volume, right? You can take rho out. Why? Because it's incompressible. And then you're going to be rho times integral volume. What's the integral of that volume? The volume, right? Volume of this cylinder, right? And then I have ddt of that. Again, you can take the rho outside of this, but you have rho dv dt. Can I say the rate of volume change is 0?
No.
No, I can't say that. Because it's just compressing, the moment you apply force here and it goes down, the moment you have kinematic here, there is a kinematic here, and there is a compression here. So you cannot ignore that. So you have to take this into account. So rho times the derivative of volume plus, now this integral. Again, can I take rho out for this problem?
Yeah.
The density is constant, you see? The reason that we get density constant, because the fluid is not going to compress the air. It's going to exit. So the density is same. So I can take rho out, and then what do I get? Integral v dot n ds. What was that? I ended up with that. So plus, let's do this integral. There is a rho inside this integral, v dot n ds is equal to 0. Now, your equation is simplified to that. Now you can see I got rho on both sides, right? I can get rid of it, but rho is just cancelled out, divided by rho. It just cancels out. So what do you get? dv dt plus surface integral v dot n ds must be 0. Alright? So let's evaluate this integral together. How many faces do I have on this? 1, 2, all the sides, 3, 4. This also 4. Right? It's a whole. What do you integrate over that? Because the system control volume is the cylinder. See this dash line is passes through that, so you have to integrate. So I have 4 faces. What do I get integral over all these faces except this one? 0. Why? Because the velocity is 0. Then what do I get for the integral over this? V dot d. Where is my normal vector? Normal is this way. Do you see that? So if I say v dot n, what do I get? This is your V, right? Let me draw it here. This is your VB. This is your N. So if I say V dot N, what do I get?
VE,
Huh?
VE,
Let's do it together. V E dot N. That will be magnitude of the first one times magnitude of the second one times cosine the angle between them. What's the angle between them?
0,
0. So what do you get? That's VD,
Just VD.
right? So this guy over that surface, V dot N is what?
VE,
VD. So you can, this integral, when you do that, after you do that, the integral, the entire integral, become what? VD times?
DS.
But when you do the whole integral, what do you get? VD times? What I want, taking the integral? Yeah, pi r squared. You see, there is an r here, radius. I think I did RD. Didn't I give you RD? Yeah, D. Yeah. So the radius is 0.5 centimeter. Are you guys following this or not? I see some of you are following it, but some of you are not following it. You really need to put, we get videos here and we post it hopefully soon. We need to really follow because this is just the easiest part of this class. Then we have next chapter is momentum, and then we have energy, and then if you understand that, the rest of it is piece of cake. But if you don't understand this, it's gonna get even harder. So for this area here, after you do this integral, you end up with this equation right here. When you finish this integral, you get that. You take dv dt plus the surface integral v dot n ds is 0, it's continuity. Then you get dv dt plus this guy becomes dv times the area of just this outlet, which is pi r, which is d over 2 squared. And it's positive because the dot product is positive, 0. So that's your equation. Now you may say, well, it still is not useful. I need to relate it to the velocity at this point. Alright? So how can I do that? Look, what is that? This is volume, right? I should have put this dash. This is volume, this is not velocity. This is the volume.
But couldn't we find the change in volume?
Yeah, you see the volume is what? Let's solve volume. Volume is what? Volume of cylinder is what? V here, which is what? They,
Pi r squared.
yeah, it's pi, let's do parametric. So it's pi, the capital R, which is in this case 1 meter, right? The square times h, right? Now if I take derivative of this with respect to time, let's say I take derivative of that with respect to time, what do I get? dv dt with respect to time, what do I get? Does the radius changes versus time? Let me ask. Does the radius changes with respect to time? Yes or no? Yes or no? No. So I get what? I can take it out of the derivative. I get pi r squared times dh dt, right? Is this 0? What is dh dt?
Longitude times the velocity at c divided by 4.
What is dh dt? Look at it. This is fixed. This is fixed. dH, the change of this versus time, what is it?
0.25 centimeters per second. It's a change of
Which is
The velocity at A.
VA, the velocity at A, which is the same thing we said. Well, I just wanted to get the formula, so this guy is thus VA. So the end result is dV dt, the change in volume is volume again. dV dt is equal to pi r squared times VA. Yeah, is equal to pi r squared VA. You now substitute it here, you get what? You get pi r squared VA plus VD pi d over 2 divided by 0. Here we got 5. So you get what? We get the relation between VA and VD. So look here, I wanted to find VD, right? I wanted to find VD. So I solved that for VD. What do I get if I solve that for VD? You get VD is equal to negative r squared over 4d squared times VA. Yeah, good? Take this to right. So it's a negative r squared over d squared, but you bring the 4 up times VA is VD. Now I have this, I can plug the number here. For R, I have V, but what should I put for VA? What should I put for velocity at this point?
well, because it's a lever, you just
Yeah, you see, just take this part, I'm gonna draw it here. This part here is ground, here is fixed. So it's going to rotate about that point. So this point, let's call it Y1, call this Y2. Or if I move it down, I should have gone the other way. Should have gone the other way. So this goes this way, down, and then goes here. Right? This is d theta goes down, so this is y, call it y1. And then d theta, call this y2. So these two triangle are similar, right? Why? Because it's d theta. So this distance from here by this, y2, whatever that distance is, what was that distance? That distance was 1, right? So 1, yeah, here. 1 divided by y2, right, is equal to what? 4 divided by y1. So you have inverted, y2 is equal to y1 divided by 4. Take derivative. dy2 dt is equal to 1/4 dy1 dt. So what's dy2 dt?
1.25.
Point, yeah. So here, if you write that, is dy2 dt is 1/4 dy1 dt. dy2 dt is the velocity of here, dA. And dy1 dt is what? Velocity at C. So instead of VA, you could just use this relation. Instead of, you don't put VD, VA. It's VA. So instead of VA, you substitute that. So you get final result, VD is equal to negative pi 4 r squared v squared for V8. We just put 1/4 VC. Just wanted to find the parametric closed form solution. But you could just use the calculator, like you said, 0.2, 0.1, do all the calculation, and that's the final result. Now, when you plug the number in it, let's plug the number in it, you see that velocity is negative the other one. What does it mean? Because you see this mechanism, when one side goes down, the other goes up. So the direction is negative. Also, dHdt is what? The expanding volume. Is if you expand, it's positive. You compress negative. So when you compress that negative sign, the compression. So if you plug the number in, you get dV is equal to negative pi. For R, you get 1 square divided by, for D is the diameter of the nozzle.
1 centimeter.
1 centimeter, so 10 to the negative 3 meter square times 1/4 of VC. And VC is what? 1 centimeter per second. Is that what? Is that 1 centimeter per second?
Yes.
Yeah. So the end result, because the dimension of these two bars, they cancel out. So if you put centimeter, you get centimeter per second. So the end result is centimeter per second. Put it in. What do you get? With a calculator. Yep, negative 10,000. Negative 10,000 meter per second. Now, interesting things here. This guy goes so slow that I don't even see that I'm moving. 1 centimeter per second. 1 centimeter is this much. So in 1 second, which is this, you go this much. So it's very slow. It goes very slow. But the velocity here is 3 times the speed of sound. It's like military aircraft. First of all, is that possible to happen?
No. Because the nozzle type is okay.
Yeah, because it may or may not, depending on how you design this nozzle. If this nozzle is not designed very well, later on in compressible flow, you see that you get shock wave here, and this shock wave will break the speed. And they cause extra delta P, the pressure drop, and you never reach the velocity. Well, assuming the nozzle is perfectly done, there is no shock, yes, it can reach the velocity, but it's crazy. Now, go to your intuition. When you have, if you build that, do you really expect this to get higher than 1 meter per second, 1 centimeter per second?
Because when it just compress.
Yeah, but look, this is a tiny area. This is a large area. 1 meter is this much. That's just the diameter. Now that's just the radius. The diameter is this much. So you have a tanker of this much, and height is this much, and then you apply this force with this mechanism, 4 meters. That's a long distance. So if you expect the end result of this huge projection velocity, but nobody expects this one. You only want to get it when you do the computation. You don't do computation, you never get it. Questions?